Okay, so I'm sure you all have been bombarded with my emails, with my announcements about what's happening with Gradescope. I just want to make sure all the ducks are in a row before that Thursday exam. So I'm not going to waste too much time right now in class talking, like reciting everything that I wrote in the big Canvas announcement. So I just ask that you read that. But the biggest thing is that just start making your Gradescope account and start that homework. The homework assignment I posted last night, it's 3 questions. It's very short. I'm sure you all can do it pretty well by now. Um, and the most important thing is if you do not have the resources at home, if you don't have a, a phone or a scanner or anything that can help upload documents, please let me know. We can figure a solution out. I want to be accommodating for. I don't want to assume anybody has a smartphone or anything like this. So just read that announcement, and that'll be the end of it. Okay. There's a lot going on, and it's hard to keep up. I'm sorry about that. There's a lot going on. But what we're going to do today is we're going to as I have written right here, we're going to finish up scalar line, not curves, integrals, scalar line integrals. And then we're going to move on to talking about parametrizing surfaces. So line integrals. There's only one more example that I like to show you all. And it kind of helps illustrate or shed light on parametrizing curves in a new way. So I'll give you a refresher. And I'm using a new pen, so hopefully it doesn't get all stuck like it used to. I don't know if you notice it, but the pen's very nice. It's a Logitech crayon. I really like it. It's like a wannabe Apple pen. Okay, so from Friday, here was the following data that we had. What do we have? We had a parametrization. So we had a parametrized curve C. It was kind of given by an R of t, where t was in some interval from A to B. And we found that the length of C was equal to, well, we wrote it symbolically as the integral of the constant function 1 over the curve with respect to arc length. And after you kind of plug in all the data, what that really looks like as a setup integral is an integral from A to B, and you're taking the magnitude of the derivative and you're integrating with respect to time. And you're doing that on that interval from A to B. And I kind of want to show like a different way to see this. So what you have, I'm going to draw the time interval A to B. This is A to B. I really want you to think about this for right now as like a physical object. Think of it as a flat a flat single-dimensional straight segment. Think of it as made of maybe some material. Maybe it's made of some like a piece of rubber, flat straight piece of rubber or something like this. And what you can think of your parameterization, what this does is it sort of actively takes that single-dimensional interval, and it kind of strews it about 3D space in as some kind of wacky curve. Maybe it's being a helicoid, or maybe it's doing some sort of it's being a circle, but it's some curve in 3D space. And this would be, you would call this would be R of A, and over here R of B. I really want you to think of parametrizing as picking up an object and stretching it and putting it and arranging it in 3D somehow. Okay, so this is the R is doing. That's the kind of action. It's taking my thing and it's strewing about in R3. This is in R3. And I'm going to kind of say a little bit more about why this makes sense in terms of the length. So on this next page, I'll show you what, if you really think about it, if you really think, well, why does it make sense that we're integrating the derivative, the length of the derivative from the interval a to b? Like, why does this make sense as a length when we really understand this integral as something from calculus 1? So why does, I guess, why should this intuitively describe length of C? So I'm actually going to go ahead and write down here, draw the theoretical. So here's the interval from A to B, and maybe the curve that we're integrating, which is this thing right here, maybe it looks something like this. Maybe it's kind of like that. So I've literally drawn a function of t, and what's that function? That function is really the speed of how fast the parametrization is going at a certain time t. And how you can kind of think of this is, this function is telling you, if you want to chop up your domain into a bunch of small pieces, then the height of the function is telling you how fast that segment is moving. Really, the height is telling you how much to stretch that individual segment. So like right here, I'm seeing maybe some low values of this function. And because this is low, sort of the instructions for constructing my curve say, okay, this blue segment down here is low, so when I move it over into 3D space, the blue segment doesn't really get very far. Maybe it only goes about this far. However, later at a different point over here, when my curve is going very fast, that tells me that this little segment is worth a lot more because the curve is going much faster. So maybe that segment over there might look like a much longer curve. And in fact, the height of that function is instructions for drawing the rest of the curve. And so in some way, so like I've kind of drawn a piecewise, this over here is the curve C, and this again, this would be like R of A, R of B. So the height of this function gives instructions on how to sort of build the curve lengths at each t value. Another way to think of it is the function is telling us how stretched the segment is, the interval from A to B, at each t value. So it's sort of telling you like geometrically at each point, how do we stretch that as we move along? Sort of integrating it is going to give us the full length. So I'm going to do a very explicit example of something like this, because I don't know if you remember, but every example we did on Friday of a parametrized curve, and we found the ds, we found ds is like we always found it was some number. We found it was a constant number times dt every single time. And I promise that wasn't the case. That wasn't always true. It just happened to be the case that we were cooking up parametrizations that moved around the curve at unit speed. So I'm going to give you one example of something that doesn't quite do that. Okay. I'm going to do basically everything on that previous page, but I can't understand the sentence gives instructions. So what I mean So Nicole asked a question about what gives instructions. It's sort of like, so I sort of think of the parameterization is, if I were in the room right now, if we were all in a room, you could see me, I would be putting my hands over this interval. And I would say what the parameterization is doing is it's taking that segment and it's using its hands and bending it and stretching it around 3D. And like if you wanted a set of instructions on how to bend it, this function is telling you explicitly at each piece how much should I stretch the plastic. It gives instructions. Maybe that's not the best way to say it, but it's just telling you, it's telling you how to stretch the curve around is kind of all I mean. This is all loosey-goosey. None of this is, I'm just trying to give us, yeah, I'm just trying to give a feel. And maybe things will make more sense after this example. So here's just an example, and after this, we'll move on to parametrizing surfaces. So we will do, r of t is not cosine of t, sine of t, because we know that goes at unit speed. We're going to do cosine of t squared, sine of t squared. So this actually moves faster as t increases. So I'm going to let t range between 0 and the square root of 2 pi. And the picture that we'll see is the following. So here's that interval going from 0 to 2 pi, the root 2 pi. And the parameterization is going to pick up this thing right here. Oh, and check out this tool. This is a very nice tool. We can actually draw a circle and it will correct it for me. Yes, nice. Okay, so what does it do? It will send, okay, I'm gonna use a whole bunch of colors right now. So we're gonna start with, it's gonna start here. So this is 0 and it will take us to, let's say, this is r of 0. I'm going to cut this up into segments over here. So I'll do fifths. And I need to write 4 of these, I think so. Or 1, 2, 3, 4. Okay, so on the left, I'll have evenly spaced intervals, evenly spaced segments. I guess I'll call them segments. But on the right, they won't show up as evenly spaced. They'll be moving faster. So the pieces over here are going to be worth more length. So I'll use sort of a chromatic progression because I like this. So that was red, this one's purple, and it will take us maybe to right here. Okay, maybe that's r of root 2 pi over 5. I'm just kind of guessing. I'm really not being precise. This is right here. This is a root 2 pi, 2 root 2 pi over 5. And that might take us up here. This is r of 2 root 2 pi over 5. What comes after blue? Well, green. So that's maybe 3 root 2 pi over 5. And that might take us over here. So as you can see, we're starting to get faster as we move around the circle. I'll even write it down. R of 3 root 2 pi over 5. And finally, maybe if we get down here, what's after green, orange, or yellow? So maybe this is that last piece. So you can see that this interval kind of gets mapped to this full interval. So R is totally stretching that last piece by a ton. This yellow piece is worth a good chunk of this circle, whereas this red piece really wasn't worth that much. And so let's actually see how everything turns out while we find ds and find the length and everything. So let's find the derivative. R prime of t, well, if you believe me, that'll by product rule, by chain rule, I'm going to have a 2t is going to pop up out of both components, and I'll get negative sine of t squared and cosine of t squared. And to compute the length of the derivative, well, this number just pops right out. So it's 2t times the length of this. But this is going to give us a sine squared, cosine squared type thing, and this just becomes 1. And so the length is 2t, or the speed is 2t, meaning as as t ranges along this interval, we get faster and faster. The t is increasing as time increases. So it moves parabolically. It sort of moves like x squared. Okay, so let's find the length of this thing. The length is equal to, and I'll actually draw it up here. This is the function 2t. If the bottom axis is t, then this up here is 2t. So the length is the integral over c of the constant function 1 ds. And we found this is the integral from 0 to root 2 pi of, I'll even draw it as this function right here. This is 2t. We're literally integrating 2t over this integral dt. And that's you've probably never seen it like that. So I'll just write 2t. And let's see what happens. When I integrate this, reverse power rule gives me t squared over 2 times 2, evaluated at root 2 pi, 0. Lo and behold, we get 2 pi, which is what we know the length to be. But basically, it's like, even though we went at different speeds, it was telling us that, weight that yellow piece quite heavily because it will be moving very fast. It would be worth a lot of length because it's moving fast. So that's kind of what I want to say about the last bit about parametrizing curves. And because I really wanted you to think about a parametrization as taking that segment and stretching it around in 3D space or 2D space. Okay, so I'm gonna totally move topics in a sec. Okay, it took longer than I hoped, but that's actually okay. So now we're gonna start parametrized surfaces. Okay. So we've talked about surfaces in a couple different ways. We've talked about it in only one way. We've kind of, we know how to talk about the equation of a plane. Remember, equation of a plane was something like ax plus by plus cz equals maybe, I don't know, 0 if it passes through the origin. Or a sphere was, x squared plus y squared plus z squared equals some number squared. The commonality with all of these is it's one equation in 3 variables. And this creates a 2-dimensional surface in 3D space. So we're going to find a different way and kind of a more hands-on and involved way of describing these things without it's going to be a different perspective. Okay, so I want to remind you what we have when we have a parametrized curve. So what is a parametrized curve? Because if we have good intuition about what R of t is, we'll get a good intuition for what a parametrized surface is. So remember, this is an R of t, which has 3 components: an x of t, a y of t, and a z of t, where t is between some set of numbers, a and b. What I want you to notice right here is you have one single input, and what it produces for you is 3 outputs. And so what you should think of this is like describing for you geometrically is, thus R describes a 1-dimensional object in a 3-dimensional space. So to do the same kind of thought process, to have a 2-dimensional object in 3-dimensional space, we'll have 3 outputs, like where we see that purple. We'll have 3 outputs, but we'll need to have, instead of 1 t input, we'll need to have 2 inputs over here. So instead of r of t, what we'll have is an r of uv. So for surfaces, which are 2D objects in 3D space, what we'll have is an r, and I'm gonna change the variable. I don't like to use t. I really like t for when I am talking about a single variable input. So I'm gonna use the u and v. I like u and v because they really are a pair. They're a set of twins. Those letters really are so similar, and I like to use them, and other mathematicians like to use u and v to denote, to sort of help the reader know that you're using a 2-variable input. So like this is 2 inputs, and this should be an x of uv, a y of u of uv, and a z of uv. And this is going to somehow trace out curves. Sorry, this is going to somehow trace out surfaces in 3D space, much like this was tracing out a single curve in 3D space. Okay, and then often you're going to have your u between some bounds like a and b, and your v might be between c and d. Just like over here, you had parameter bounds up here, you have parameter bounds down here. Okay, so I'm going to move to the next page, and the rest of the day is just going to be examples after example after example. So I mean, if we have enough time, 25-ish minutes, we'll do spheres, parabolic bowls, cones, cylinders, you name it. All the good pictures that, all the surfaces that we've done so far, using, we've been able to describe using in a different way. This is a second way to describe these things. Okay, so let's do our first example. And I'm thinking about this. I'm probably going to, I'll say it later after you have some appreciation for what we're doing. So let's do r of uv. If I'm going to tell you what it is, I need to tell you the 3 component functions. I need a function here, a function here, and a function here, all 3 involving the variables u and v. So the first one's going to be a cosine of u, a sine of u, and a v. Okay, and I'm going to let my u go between 0 and 2 pi, and my v is between -1 and 1. So the big question is how to visualize this. I promise that all of you have seen this shape before, but probably none of you have seen it described this way. And to do this, what we'll want to do is we'll want to hold some of the variables constant and see the curves that it traces out. So I'll show you what I mean. So over here, I sort of have this chunk of UV plane. This is, let's see, this is sort of like my V, and this is my U. Think of it as like an XY plane, and I'm really using these right here. So my U is going between 0 and 2 pi, and my V is going from -1 to +1. Okay, and what I'm going to do is I'm going to have I'm going to write my blue horizontal strips, my U horizontal strips as blue lines, and my vertical V lines like this. Okay, and so like before, the parameterization picks up So what R does is it takes this sheet, this rubber sheet, and it stretches it and pushes it around in 3D space, and it's going to give us a surface. And to figure out how, it's helpful to hold, for example, like V constant and see what these horizontal lines trace out. So think about fixing, so fix V and see the curves traced out. So for example, let's do, for first example, so I'm going to draw 3D space. I'm going to draw the curve we get. It's a one-dimensional object that we get from V equals 0. We're looking at R of u comma 0, and this is just cosine of u, sine of u, comma 0. This is a curve, and this is a one-dimensional object. It gives us a circle of radius 1 centered at the z-axis of height at height 0. So that gives us this curve right here. So like this, basically R takes this, I'm highlighting something in the UV plane, and it takes it to this circle. Okay. If I want, let's say I want to do V equals 1 for a second, so I'll do that in a slightly different blue. Maybe this one up here. I want to see where does R take this lighter blue curve. Well, it's going to be V equals 1. R of u comma 1 is equal to cosine of u sine of u, but now my height is fixed up here at 1. So I get the same picture. It's a circle of radius 1, but now it's up here at height 1. So I've got this sort of cylinder, this circle. Oops, I said it. I said the answer. And down here, it'll take this lowest curve is down here. So in fact, what we'll get is it takes all of these horizontal blue lines in that UV chunk of rubber to these horizontal circles here. Sorry, yes, these horizontal circles. And you can even check if I fix things the other way. If I fix, so let's say I want to fix, let's do u equals 0. Well, what do I get? I'll be feeding in just v's. So I'm looking at r of 0 comma v, and this gives me cosine of 0, sine of 0, and my v ranges freely. And if you can see, this is 1 comma 0 comma v. This is a line segment. Starting here and running vertically. And in fact, all of these vertical lines in the UV plane, these vertical purple lines, will get mapped to these vertical things up here. And you see we're starting to trace out a cylinder. And indeed, this is the case. So this is a cylinder of radius 1 between -1 and 1. That's the object that we get. Okay. We're gonna do more examples, and we'll kind of be doing it in the same way. So if there are any questions about how I sort of assembled this picture, now's a good time to ask. Kind of what I did is like I saw exactly how the R was taking this and how it was spinning it into 3D. And to do it, what we did is we sliced the two-dimensional region into single variable strips, and we relied on our previous knowledge of how to parametrize single variable things. Once we got a couple of the single variable curves, we realized we could stitch the whole thing together just be kind of by our intuition. So I'm going to move on to this next page. I'll give you another example. So that was a cylinder. Let's do this one. This one's great. So this is another. So just geometrically, so describe the parameterization R of U comma V equals V cosine U V sine U V squared. So this is like, this is my X of UV, okay? And Y of UV, Z of UV, right? I have to tell you the three component functions. Again, my two inputs and my three outputs. That's a parametrized surface. I should probably tell you, sorry, my parameter domain. So I should tell you my U's, just like last time. Notice where my U's are. They're on the inside of the trig. So that kind of tells you U might be playing the role of an angular coordinate, like a theta. So, and indeed, another hint at that is U is running between 0 and 2 pi, just like it was before. And in this case, I guess my, yes, okay. And then my V is ranging between 0 and 2. Okay. So again, I'm gonna draw sort of this in the UV, this chunk of UV plane. So here's U, here's V, here's 0 to pi, and 0 to 2. Again, I'll see how R maps the horizontal blue strips, and then maybe I'll see how it maps the vertical strips. Okay. Are the ranges given? Yes, the ranges are right there. Good. And that's always important. That's typically important. That's good. So let's see. Again, when we get horizontal lines, let's just look up here and just kind of convince yourself what happens for the horizontal blue lines. Now, again, if the V is fixed, what we see is that height will be fixed, and we'll have a circle of radius V. So I'll say note, blue line segs. This is constant V, map to horizontal circles of radius V and height was Z is height of V squared. So let me draw X, Y, Z. And what I'm going to do is maybe I'll draw this one for a second. That one is, say, at height V equals 1. And that will go to, I'll be very careful with my, so this will be height 1. No, I don't want, height 1 is down here. And I'll have a circle of radius 1 centered at that height. So this maps to this piece. But now up here, this one is going to be higher up. So this V equals 2 is going to map to a circle of radius 2, but super high at height 4. So in fact, this is, if that was Z equals 1, Z equals 2, Z equals 3, here's Z equals 4. This topmost, I'll do it in the light blue, actually. This goes to something more like this. So I've only drawn 2 circles, but can anybody take any educated guess as to what the full surface might be? I'll give you a hint. It's rotationally symmetric because it's made out of circles. But why don't we take some guesses in the chat? It's an object you have seen: a cone, a parabolic bowl, and a cone. Okay, it's 2 right answers and 2 wrong answers. It's a parabolic bowl, but the cones weren't bad guesses. People are probably saying cone, but the reason why it's not a cone is because, let's see, I'm looking over here, the radius and the height. If it were a cone, the radius and the height would be linearly related, but they're related by a parabolic factor, like it's an x squared. So in fact, it's going to be tracing out a parabolic bowl. Exactly. Good. And what do the V strips look like? They start down here at 0 and they move up. Like, think of it as, so this is here was radius. This is v equals 1, so radius equals 1 and z equals 1. Let's think. This is probably, that's v equals 0.25, so the radius is, no. I'll say that might be v is 0.5, so the circle in question, this circle, might be radius 1/2, and height is 1/4. And then by the time I come out here, that's my v equals, let's think, v equals 2. So the radius is 2 and the height is 4. So it's kind of this parabolic thing that's happening. Exactly. And they move up, right? This was v equals 0, 0.5, 1, and 2. So that's kind of what's happening here. It's a parametrized surface. And because like we have all these points in the parameter domain, and the parameter domain get pushed off into this surface in 2D space by our parameterization R. Think of your R as your little working elf, and your elf is like assembling this piece of rubber out of these instructions, sort of telling you what to do with that blue and purple fabric. And it's time to build something. And so we're going to keep doing some more of these examples, but you might be wondering, well, this seems really complicated. Like, you might say to yourself, this is a lot of text. That's a lot of extra variables and stuff. You could say, why can't why is that superior, or why are we doing this when I also know that a parabolic bowl is also, let's think, z equals x squared plus y squared. Like, hang on, I thought this was a parabolic bowl, and this is way simpler, right? Well, it turns out if you want to do integrals, okay. Here's the point. I think somebody asked a long time ago when we were describing triple integrals, and I'm moving to this next page. Here's just a total side note. You can talk about the sphere as, x between 0, -1 and 1. Y, you don't need to write this down. This is stuff you already know. Y is between -√1 minus x squared, and then √1 minus x squared. And then z is between, the super huge mess, √1 minus x squared minus y squared, 1 minus x squared minus y squared. And this was the sphere. And somebody asked the nice question, well, why are we doing it like this when we can seriously just write this? Isn't this somehow superior to this? And I said, yeah, this is short, condensed, and probably cleaner, easier to look at than this absolute eyesore. But when we wanted to do integrals, this is how we needed to feed the data into the bounds for the integral. And similarly, like over here, the integral is not really going to understand this so much. It's going to understand this kind of data. So that's where we're going with this. And that's kind of why I want to set this stuff up. Okay. All right. So what's my next thing? All right. This next thing I want to say is, what's a commonality between the last two examples that we did. So I want to show, let me see, where's my black? Here's my black. Okay, so note both previous examples were of the form, they both have this like cosine thing in them. They were both like a foliation of circles. It's a r of uv. They both looked like some f of v times cosine of u, that same f of v times sine of u, and then some g depending only on b. So let's just go back. Let's go to the previous section. I want to figure out what the f was and what the g was. What was the f? What was the g in the previous? In the previous, our f, it's the thing that you can find right in front of the cosine. So that was just a v. So that was f in our previous case. And here was our G in our previous case. And over here, here we had, think of a constant 1, that's like your F, constant 1. And this over here was our G. So I kind of want to show you what to do in general when you notice a pattern like this. This is essentially telling you, this tells you that constant V pieces give horizontal circles of radius F of V and height G of V. So this tells you, or this hints at, this hints at rotational symmetry. So draw object in RZ plane. And so what you'll have in the RZ plane is a single parametrized curve. So you'll have your R and your Z, and I'm really, this is unfortunate. This, it means R in terms of radius, and different than like that vector R. Those kind of mean different things, but I'm realizing I'm running into the same notation here. Different R. So I'll do my best to put the hat over the thing when I mean that when I'm referencing the vector valued parametrization. Okay, so what we have in here is I'm gonna highlight that, highlight this. These are the same thing, and this. So notice that we have F of V is R, and G of V equals, let's see, Z. So again, one input, two outputs. This gives a parametrized curve in the RZ plane. So in example 2, we had R equals V, Z equals V squared, and this gives a like that parabola that opens up like this. This parametrizes that parabola, and really the object we got was swinging it around. And in example 2, in example 1, we had R was equal to 1, and Z was equal to V. And if you look in the RZ plane, in fact, here, I'll do it to match the color. These were like purple. Yeah, these were purple. And those are the purple things that we rotated. So over here, this is the RZ plane. If you think about what this parameterizes for you is a single vertical line segment at R equals 1 and goes, and our parameter domain had us ranging from V was -1, our height was -1 up to +1. And that's the thing we rotated around to get our cylinder. So this is a great way to parametrize rotationally symmetric objects. So this is your bread and butter, how to parametrize rotationally symmetric objects. So let's go the other way. So I'm gonna, let's see. I'll write what's in that purple box in this next page, so don't worry about rewriting that. Okay, so I'm gonna go to this next page, and we're gonna ask ourselves how to, okay, so let's do, I want to do the cone. Should we do cone or sphere? Let's do cone. Let's do cone. Okay, so example, parametrize. So now we're going to go the opposite way. We are going to come up with the parametrization for the cone. So parametrize the cone, the cone Z equals 2 root x squared plus y squared, and this is just z equals 2r. So before we even start parametrizing it, I'm gonna, it's rotationally symmetric. Let's draw it in our favorite RZ plane, and I'm gonna draw 2r, and that just takes off like this with slope 2r. Okay, this is z equals 2r. I'm gonna write that formula again. So r of u comma v should equal f of v cosine u, f of v sine u, and g of v. So it's where, we'll look for these functions describing this purple curve, and then we'll be able to just set the whole thing up by using this kind of rigid formula. Okay, so, and this is again, this should be making you think of cylindrical coordinates a little bit, because what you'll have here in cylindrical coordinates, remember this was x, this was y, and this is z. And then cylindrical coordinates, x is r cosine theta, y is r sine theta, and z is just z. So kind of what you're seeing is that, f of v is playing the role of r. I'll do this. Oh gosh. Okay, I want to use a different color. G of v is playing the role of z. And then what's my last, what I want to do? Let's say blue. And then u is playing the role of theta. It's a whole bunch of different ways to look at all these things. But let's just come back to this equation, this up here. Let's describe that parametrically. So describe this slope to ray using a parametric equation with time parameter v. So you'd probably be used to this using a t, so time parameter equals to v instead of t. It's really going to be the same thing. So if you want to parameterize that line segment, you'd probably, if you probably would have done, if you were using x's and y's, you'd say x equals 0 plus 1t, y equals 0 plus 2t, because you know how to parameterize line segments pretty well by this point. But this is not x, that's r. So I'm going to write this is r, and this is z, and instead of t, we're using a v. So I really want to emphasize that you've seen this before. So it's really r equals v, z equals 2v. This is my f of v. This is my g of v. And so our final parameterization, so final answer is v times cosine of u. I'm just writing where that r goes. I'm really using this structure up here. V times sine of u, and then 2v. And then I might just emphasize that my u goes from 0 to 2 pi, and my v, I definitely want to start at 0, but let's just say infinity to do the whole infinite cone. And this is the parameterization of that cone. It utilizes the rotational symmetry and utilizes sort of the cylindrical coordinates. Oh, and it is like time to go. There are tons more examples I haven't done. Okay. Okay, I'm going to turn off the, okay. Okay, no, I'm not cancel. I'm going to stop recording.